these all mean the same thing. So if I'm looking at average rate of change, slope of the secant line, or average velocity, and I'm talking between 2 points, A and B, right? If I have the y value for B is f of B, the y value for A is f of A, that line, remember, between 2 points is a secant line. So the slope of the secant line will be the change in the y values over the change in the x values. So now if this is given in time, where I'm talking about the function s and t is in time, and I want to find the average velocity, you know that means change in distance over change in time. Change in distance over change in time. S of B minus S of A over B minus A, right? So it's the same thing. So don't want you to get confused. They all mean the same thing. So now let's look down here. So this is just using two different x values of A and A plus H. So this is still the same thing, change in the y values over change in the x values, and you can see that A plus H minus A gives us H, and that's what the denominator is. So slope of the secant line or average rate of change, those are the same. Now, if we're looking at a position function s of t, that changes our x-axis to t because we're in time, but it's not any different. So if I go to s of a plus h, subtract off s of a, divided by s of a, divided by a plus h minus a, that gives us h, that's the average velocity. Okay, so let's go forward and look at lots of these pictures. So I'm looking at the function x cubed. So for the function x cubed, I'm using the point P as 1, 1, right there. And then I chose a point Q as x equal 1.5. So here's x equal 1.5, and I drew a line between those 2 points. And so that's the m sub pq, slope of the secant line. And so that gave me 4.75. That's the slope of that dotted line. Let's move to the next picture. Now what I'm going to do is I'm going to still keep that point 1, 1 there, and I'm going to move that, instead of 1.5, I'm going to say, let's find out what the slope between 1 and 1.2 is. So I put 1.2 into the cubic function, right? Remember, because that's what I'm using. I'm using f of x equals x cubed, and I get this y value. So the change in the y values, that's what the numerator is, right? Divided by the change in the x values, I get this. So this is the slope. So I've got this slope for that one, this slope for this one, and I'm just going to kind of rush through these. So I chose 1.1. And so I take the change in the y values over the change in the x values. That gives me this slope is 3.31. Oh, and I got super close. So in this last one here, I got between 1 and 1.01. I drew it much bigger so you could see it, right? So change in the y values over change in the x values, so I get that slope. Let's see if those numbers look like they're going anywhere. Maybe. Okay, so let's go back and look at what we've got over here. So now what I'm doing is saying I still want to keep x equal 1, but then I want to go backwards. I want to say, oh, let's start it from this point back here. So I go to find that y value, again, by plugging it into the cubic function, and I can see the slope of that line will be change in y values over change in x values, so I get 1.75. I do the same thing, only I'm not using 0.5, I'm using 0.8. And so that 0.8 is getting closer. Do the same thing, change in y values over change in x values, I get that slope. Then if I chose 0.9 and put 0.9 into the cubic function, I get this. So this slope turns out to be this. So can you see what perhaps the slope of the tangent line would be? So the tangent line, I know you learned this way back in geometry, at x equal 1 means you're drawing the line that just touches that one point. And it doesn't matter that it crosses there again. Doesn't matter. Doesn't matter at all. This slope of this line, the line that's tangent to the curve at x equal 1, since these numbers are getting close to 3 and these numbers are getting close to 3, I would guess that the slope of that line is 3. And since we were approaching from the right and the left, you know that that sounds like a limit. And so that's how we're going to get this next definition of the derivative.